summarize my role at Oxford Nanopore in 4 words: making read processing fast. And I'm going to go into that today. I'm going to show you a bit of, that. Okay, right. So I'll give you a bit of background first, and I'll touch upon how we use GPUs in Dorado, and at the end of the presentation I will give you a bit of a summary of where we're currently at and what we'll do in the future. So as a background, Mark's already mentioned base calling, and I guess most of you will be familiar with base calling. What it is, interpreting the read signal is hard. That's why we use machine learning methods. This works because of something called the universal approximation theorem, where it is possible that a deep multi-layered neural network can learn almost any function that is useful and learn to approximate it to a high accuracy. The drawback of this is that these machine learning models are computationally really expensive. So, for example, our current hack model, it uses 2.6 million operations per raw signal sample that comes from the machine. And given that a PromethION 48 has 48 flow cells, it can generate up to 720 million samples, reads like signal samples per second. That together means more than 250 operations per second are required to process the read signal, and that requires a supercomputer to keep up. Don't you think? Well, actually, GPUs can help us there, and a GPU is a graphics processing unit. They've evolved from 3D graphics accelerators, which became really popular in the 90s. And they're designed for interactive 3D graphics, so basically often video games. And yeah, that's really the kind of main motivator, is to make video games look good. One key thing there is that they're highly parallel, and initially those accelerators were fixed function. You couldn't really use them for anything else, but gradually in the 2000s, the flexibility that was required to make graphics better then led to these devices actually being useful in scientific computing, physical modeling, all these things. And at a certain point, AI researchers realized, oh yeah, these devices are really good at accelerating neural networks. And from that point onwards, neural networks became really impactful, had a massive success. And it turns out that now GPU companies actually have adopted that and designed their GPUs to be really good as deep learning accelerators. To show that in numbers, for example, this is progression of NVIDIA data center GPUs. 7 years ago, we had P100 here. That's the Pascal architecture. It provided roughly 19 tera operations per second. That's 2 to the power of 12 operations. 2 years later, the Volta architecture introduced tensor cores. These are matrix multiplication accelerators, and that led to a 6 times improvement in peak performance here in using 16-bit floating point numbers. Then Ampere architecture 2 years later again gave a massive improvement in performance. And I'd like to highlight these 2 numbers here. So we were with the Volta V100 architecture. That's kind of where we focused with Guppy. Now with Dorado, we have find a new kind of focus where we use 8-bit integers on the Ampere architecture, and it's again roughly a 5 to 6 times improvement in peak performance on these GPUs. Now, realistically, we don't really achieve the peak performance, but we get a massive improvement. there. Um, oh, this is right. Now I'd like to talk a bit about how we use GPUs in Dorado. So Mark already mentioned that we use the Torch library. We have many reasons to use Torch, but there's one thing that actually Torch isn't entirely great at, and that is performance in specific cases that we use. So there are some operations where we really need to kind of use hand-optimized code, and that's especially true for our LSTM layers, and I'll go into that. LSTM is a recurrent neural network layer, as Mark mentioned. We use them, and LSTM for us is really the core component of our base call models. So they are the most computationally expensive part of our models. We spend most of the runtime there, and they are capable of making sense of long-distance relationships, which means that there's a serialized component where this layer steps over the signal in a time-ordered fashion. And we implemented a custom type of layer for this in CUDA, which is the language and the API for using NVIDIA GPUs. So what I'd like to show here is at the top here we have an execution trace, and this is kind of a timeline. So from left to right, this is how long it takes, and this is the initial. At the top is the initial Torch built-in variant of LSTM. We had so this takes about 159 milliseconds for this specific example. We have an improved version where we used optimized matrix layouts. We used cuBLAS as a matrix multiplication library, and that improved our runtime to 103 milliseconds, so that was massively faster. But then we decided we were going to use Cutlass, which is a library provided by NVIDIA for matrix multiplication. We are combining the LSTM consists of a matrix multiplication and a gate calculation, and we're combining those into a single loop. And what you can see here is these little kind of stripes. They're all kind of individual executions of a program. And what we've done here is combine thousands of these into a single block, and that makes it a lot faster. What we also done is using quantization. So we went from using 16-bit floating point operations to 8-bit integers, and that helps us a lot in the peak performance that's available, and also in reducing the local memory utilization. So what we achieved here is a 2.4 times performance improvement, and I want to mention that we had some great help from NVIDIA. A lot of you from NVIDIA is in the audience. If you have any questions specifically about NVIDIA GPUs, and please ask. We also have a custom metal code. Mark touched on that. So I just want to quickly mention it. So that our Dorado implementation kind of predates with Torch supported Apple GPUs. We get really great performance out of the GPUs for some layers, more than 90% ALU utilization. And there are other accelerators on Apple M1 chips, which we currently don't use. We are exploring these options. Then I want to quickly go into what we need to run quickly on a GPU is batch processing. So GPUs are massively parallel, so we really need a lot of work to be done in parallel, and we do that by taking multiple reads. They're already independent work items. We chunk them into fixed size chunks, and then we collect these fixed size chunks into what we call a batch. And these batches can be thousands of chunks, really. That could be 6,000 chunks or so. And getting the numbers right is really important for high performance. So what we've done with Dorado is an automatic batch size detection. So when you run Dorado with the default setting, or you run it with B or batch size 0, it'll automatically detect the right batch size for you. There are edge cases where that might not work, but the default, we wanted for all of you to basically be like, okay, will detect automatically what's the right thing to do. And then I want to touch about, yes, what we've done in Dorado. What's new is this, what I talked about, diffused LSTM implementation, which gives us great performance. We moved to quantization FP16 using 8-bit integers now in half the neural network layers, improved automatic batch size detection, and also we added duplex calling on the GPU. It uses exactly the same code as the simplex calling, so all the changes that we do, all the improvements that we do for simplex will immediately also apply to duplex. And we are still going to further improve our LSTM layers. We still think there's some great potential there. We'll widen the quantization use. We will also investigate hardware structured sparsity, which might again give us a big boost in performance. And most importantly is that we are continuing to evolve our model architecture. So as we get faster in certain areas, we'll re-investigate whether we can do more there and improve the base call accuracy that way, and give you, like always, the best possible base calls. Thank you very much.